you don't have to go anywhere to do it. It's kind of convenient. So, well, we just started streaming live on Facebook. So I'm going to sort of do a little bit of a formal welcome. Welcome attendees. I can see we've already got a lot of people here. Thank you so much for joining us. This is Michigan Technological University's webinar series called Husky Bites, and I am the host. My name is Janet Callahan. I am Dean of the College of Engineering. I'm very pleased in a moment or two to introduce my co-host, who would then introduce our speaker. So before I do that, though, I'm going to share screen and show a couple slides. Well, I have a lot of people to thank this year for all the great work that has been being done. All right, let me get this one pulled up. You can see my dog right now. Can you guys still see me? Mm-hmm. All right, so I'm going to present. So thank you again for joining us. Tonight's Husky Bites is sponsored by an anonymous donor. Thank you so much for your support of student scholarships. And again, these have been weekly webinars, summer, fall, and spring. Our fall season will likely start the Monday after Labor Day. Yeah, no, that is the start date, the Monday after Labor Day. I do want to welcome all our educators. It turns out we've got teachers in Michigan, not only teachers in Michigan, but we have teachers in Pennsylvania who have received permission from their local superintendent to receive professional development credits. So keep spreading the word, folks. Let your teachers know that this is something that is educational and it is professional development, and it's also fun to be able to watch something like this with your family and your kids. It's free. So thank you, educators, for having joined us. It's been wonderful to have you here. So many sponsors to thank in spring. And remember, your gifts can go in support of student scholarships, which is what most of the gifts go toward, but they can also go toward your favorite department or athletic, sport or whatever it is you'd like. So if anyone would like to give to support a webinar next year, these are free, provided by the college for free, but so any donations go in directly and support student scholarships. So if you were interested in sponsoring one, just send an email to engineering@mtu.edu. And thank you again, sponsors, and especially Michael and Karen Gregory. Of course, we're free. We're live streaming through Facebook, and all of these are posted after the event. So if you know somebody who might like to hear the material tonight, you can send them a link. You can get the link by going to mtu.edu/huskybites. Another reminder, if you are an alum or your grandparents were an alum, you get to go here for in-state tuition, no matter where you live. And so you can learn more about that by emailing mtu4u@mtu.edu. And we have registration still underway for our summer youth programs. So just a little quick update about graduation. So graduation is going to be this Friday, which is the last day of classes. Wait, is that correct? Is this Friday, right? Yeah. It's going to be outdoors. It's going to be a celebratory walk. It's not really a formal graduation, but and the College of Engineering is in the afternoon part of this, from I believe 2:30 to 5:30. Oh, sorry, 3 to 5:30, and we'll be joined by the College of Business. And so our faculty will be outdoors in their robes. I will be outdoors in my robe. Please, if you've been watching Husky Bites, let me know. We're so proud of you, and we're awfully glad that we have this outdoor opportunity to celebrate our graduates. All right, I'm going to stop sharing. And so, Jared, you can go ahead and start sharing while I introduce our co-host this evening.
Okay.
So it's my pleasure and honor to introduce co-host Erik Johnson. Dr. Erik Johnson is the Director of Bird Conservation at Audubon, Louisiana. He's joining us from Louisiana, where there is no snow on the ground. So Dr. Johnson earned his bachelor's degree at Dickinson College, which is in Pennsylvania. And then he went on and earned his master's and PhD at Louisiana State University, where he continues to serve as an adjunct research faculty. And so pleased that you can join me, Erik, because I don't know very many things about birds. I can recognize a few, and that's, I can mimic a few bird calls, but you've just exhausted my repertoire. So thank you so much for being here. And I'm going to turn it over to you at this point.
Well, thanks, Janet. It's good to be here. And you're mostly on the way. I can only do those things, but maybe with a little bit more depth. So, you know, we're all birders on some level. So I guess my role is to introduce Dr. Jared Wolfe, right? So Dr. Wolfe is an associate professor at Michigan Tech University. And Jared and I go back a ways. We spent some time in graduate school together, so it's great to be able to catch up with him on this. But before that, Jared actually got his bachelor's degree at Humboldt State University, where he also earned his master's degree. And then finally, he came over to LSU, where he received a PhD in wildlife and fisheries conservation at Louisiana State University. And Jared is one of the founders of the Biodiversity Institute, or initiative, excuse me, the Biodiversity Initiative, which is a research team that does work in Equatorial Guinea. Some really, really cool stuff coming out of there. Jared actually won one of his accolades as Best Student Presentation in 2010 when he published the WRP system, the Molt system to birds. Jared is the W in WRP. So that received a Best Student Award from the Journal of Field Ornithology. And Jared is one productive guy. He has authored or co-authored nearly 60 publications that have been submitted to peer-reviewed journals and or books and or book chapters. So it's an honor to be able to share the stage with him today.
Yeah, thanks, Erik. And thank you, Janet, for inviting us. And I think this might deviate from some of the prior Husky Bites, just in the sense that my presentation is going to be pretty brief. And then we were thinking we could just open it up to a wide-ranging conversation. We can continue to talk about molts and plumages, and that's why it's awesome to have Erik here. He's just a wealth of knowledge when it comes to bird conservation, natural history, tropical temperate systems, molts and plumages, and so we can talk about those topics. But I wanted to start off with a very brief presentation, just introduce folks to some of the research, some of the more recent research that's been coming out of my lab, collaborative effort with a number of folks. And this research that I'm going to be presenting on particular focuses on this group of birds. And these are the New World warblers in the family Parulidae. And they are not just some of my favorite birds, presumably some of Erik's favorite birds. A lot of bird watchers and nature enthusiasts love these birds because they arrive back to their breeding grounds in these striking kind of gaudy breeding plumages, as you can see here. And so we are really interested in some of the reasons why these plumages have arisen over evolutionary timescales. And so that's what I'm going to be talking a little bit about here, the evolution of molts and colorful plumages in songbirds. And my co-authors here, Ryan Terrell and Glenn Seeholzer, are other kind of molt aficionados. In particular, Ryan, if you're interested in some of these topics, I highly recommend you check out his website. He publishes some really cool stuff. So when I talk about molts, and bird molt is simply the process of a regular, often seasonal replacement of feathers. It's a boring topic to even ornithologists. When we dive into it, people go to sleep. In fact, there's just a small handful of people in North America, Central America, and South America that study molt, and we all know each other. Like it's a small community. So I have to start with like a little bit of an elevator speech to convince people that bird molt is a good topic, one to study and two to present on in scientific discourse like this. So I start with this map. This is from Yale University. This is a heat map showing the diversity, the species richness of birds across the globe, where you have the deep red indicates high species richness and the blue low species richness. And for me, two patterns arise from this map. One is that there's clearly a latitudinal diversity gradient where you have biological biodiversity hotspots like in the Amazon, as well as if you go across the Atlantic to the Gulf of Guinea and Central Africa is another one, the Gulf of Guinea biodiversity hotspot. These are areas of high species richness, and as you move northwards, species richness declines. So this very striking diversity gradient. And the second take-home message from this map is birds are everywhere. Birds are arguably one of the most taxonomically successful vertebrate groups ever. You can find them on the tops of mountains, in deserts, in tropical rainforests, over oceans, in pelagic bird communities. So they're incredibly successful. And when we step back and ask why birds are so successful at global domination and exploiting novel niches across the world, it's really because of feathers. Right? Feathers are incredibly malleable over evolutionary timescales. Birds can use them for thermoregulation, for crypsis, for flying, for swimming, for a whole host of different purposes. And as they evolutionary shape these feathers, they can exploit new niche space. And then we have to ask ourselves, well, what maintains feathers? It's the process of molt. So molt is really intrinsically tied to the global success of birds as a taxonomic group. And so that's kind of the little elevator speech. Molt's really important to understanding why birds are so successful. It's also, as you'll learn shortly, very important when we try to understand what has given rise evolutionarily to differences in seasonal and sexual dichromatism or dimorphism between birds. And for this, we're going to focus in on the New World warblers, a diverse group of small songbirds that commonly migrate from their breeding grounds in temperate North America to the tropics where they overwinter. And what we find is when they leave in the fall, so they breed in the spring through the summer, they molt in the fall, they molt into this dull plumage, they leave and go to the tropics. In the tropics, some of these species undergo a second molt, where they acquire this brilliant breeding plumage, and then they return northwards. Right now, they're moving through Louisiana. I'm sure this cold front is slowing their pace northward, that we have the snowstorm right now in Michigan. But they're going to be arriving in these brilliant plumages, and presumably these are used to establish territories, mate acquisition, and facilitating breeding. So, but before we jump into the evolution of some of these molts and plumages that give rise to these differences in colors, we first have to understand molt just a little bit to know what we're talking about. So molt, as I said, is this ubiquitous and predictable replacement of feathers that birds go through about once a year. And in North America, as well as many researchers in Central and South America, they use a system called Humphrey and Parkes to classify molt. And this is very different than the majority of researchers in Europe, and it's strangely contentious about whether or not you adhere to this Humphrey-Parkes system or not. But Humphrey and Parkes were several researchers that suggested that molts are evolutionarily homologous, meaning that if you think back to the common ancestors of birds, like proto-aves, one of the first birds that has given rise to all the extant bird species across the globe today, that particular species probably went through a very simple molt. It probably replaced its feathers once a year. This molt was complete in extent, meaning that it's replacing all of its feathers. And that molt is still found in all the extant birds today. And it's somewhat true. All birds tend to go through an annual complete. When I mean complete, I mean the number of feathers they're replacing, complete to nearly complete molt. And within Humphrey and Parkes, we call this the pre-basic molt, which makes sense. It's kind of like basal at the bottom of that family tree. It's this basic molt that all birds exhibit. So within this kind of basic strategy, this most simplistic strategy that's reflected in the early ancestors of birds, you can add complexity to it. So on the scaffolding, you can have the evolution of new molts that we often refer to as inserted molts. And one of the more common ones exhibited by warblers that we're going to be talking about today are pre-alternate molts. So here you can see a bird on the top. It's going through this annual complete molt, pre-basic molts. And then underneath is a strategy where this is a chestnut-sided warbler, where in the fall after the breeding season in North America, they'll go through a pre-basic molt, they'll become drab, they'll migrate to the tropics, Central America, and they'll undergo a second molt, an inserted molt, where they become colorful, the pre-alternate molt, before they return to the breeding grounds, breed in that plumage. After the breeding season, go back to their pre-basic molt, become drab, go to the tropics, become colorful, and they'll keep bouncing back and forth between these molts and plumages for the rest of their lives until the bird dies. Okay, so these birds have this inserted molt, which is interesting, which gives rise to this dissimilar plumage coloration between the spring and fall seasons. So reasons for this inserted molt, the pre-alternate molt, there's several that have been hypothesized. One is structural renewal, particularly for birds that live in high solar environments, or they live in habitats that degrade their feathers. They may need to molt more than once a year to replace their feathers. There's also phenotypic changes, like rock ptarmigan, for example. They live in dynamic habitats where the snow is melting, and if you're retaining a winter plumage, you're going to become very visible to predators, and you can become someone's food. So you might need to change plumage rapidly. In fact, these birds are known to roll around in their own feces to try to camouflage themselves, because molt takes a little bit longer. So they'll actually try to create structural changes by pooping and rolling around their poop to try to change color quickly, because molt doesn't happen fast enough, which is an interesting adaptation, behavioral adaptation for them. But nonetheless, the phenotypic changes is another reason why birds might undergo a second molt or pre-alternate molt. And then, of course, sexual selection or honest signaling, right? Sexual selection may result in these gaudy plumages that are seasonal in nature. So when we think about wood warblers, this diversity of birds with this diversity of colorations, the conventional wisdom has been that there's differential selection through the year that has resulted in a molt that yields a drab plumage and a molt that yields a gaudy plumage. So the idea being that natural selection operates in the fall, resulting in drab warblers to evade predation, and then sexual selection will kick in the spring, which resulted in the evolution of pre-alternate molt to become gaudy for reproductive purposes in the spring and the breeding season in North America. So if this was true, then we would find a pattern. The evolution of the pre-alternate molt would nearly always result in a brilliant colored bird. But when we just take a cursory look at wood warblers in this family Perulidae, we see that that doesn't hold true. So for example, we have species on the top here like this black-throated blue warbler, which is quite colorful, and they don't have a pre-alternate molt. And of course, they don't have an alternate plumage. They're just colorful year-round. And then you have species like a northern water thrush, which they can have a pre-alternate molt, but they don't change color. They just are kind of drab year-round. And you have species like Canada warbler, where they have a pre-alternate molt, but they just kind of slightly change color. And then you have examples like chestnut-sided warbler, where they'll have a pre-alternate molt and they have extensive phenotypic change from the fall to the spring. So there's no clear pattern here. So the conventional wisdom is probably wrong. And just a couple key points about the pre-alternate molt before we move on. One, just remember that it only occurs on the wintering grounds. So it's after that long fall migration, when the birds go to their wintering grounds, do they undergo the pre-alternate molt. It's responsible for seasonal plumage dimorphism. This is actually, there's a couple like exceptions to this rule, like American redstart, which are really fascinating, which we can talk about, where the young males look kind of, they're in a female type phenotype, and then they get into fights on the wintering ground, and as they fight, they rip out each other's plumage, and that comes in black, giving a spotchy look as they return to the Upper Peninsula, which is fascinating. So it's kind of like a bar brawl that induced phenotypic change among them. But that's I think a super unique kind of example. But what we found out when we were initially interested within the system, that we noticed that there's a correlation between the extent of the pre-alternate molt, so the number of feathers that are being replaced on the wintering grounds, and migratory distance. And it looks like this. So here's this figure where on the y-axis we have pre-alternate molt extent. This is roughly the number of feathers that are being replaced on the wintering grounds. So they're becoming, more brightly colored for some of these species. And then on the x-axis, migratory distance. So there's this positive correlation that in general, the further south you migrate, closer to the equator, the more feathers you're replacing. And this got us thinking why. So originally back in 2010, 2011, I worked with Peter Pyle bounced ideas off of Erik as well. And we formulated this hypothesis that, and I'll just read it off here, that the occurrence of pre-alternate molt is positively correlated with migration, supporting the hypothesis that pre-alternate molt evolved in response to increased feather wear and was subsequently repurposed by sexual selection. So what we were proposing was that there's an elegant multi-step evolutionary pathway towards the evolution of seasonal dimorphisms, towards the evolution of these colorful breeding plumages. And the further you migrate, the more your feathers wear, the more there's a need for structural renewal. And once you get that structural renewal, that is a key innovation. That the evolution of the pre-alternate molt's a key innovation towards sexual selection, co-opting that molt and turning these birds colorful. So there's a couple assumptions here. Migration leads to more wear is one of them. We'll touch on this a little bit later. A few years later, in 2015, Simpson et al. Suggested an alternative hypothesis that the loss of coloration of warblers with the evolution of migration. And this was owing to the costs imposed by visual predators during migration. So the idea with this paper, they were suggesting that the ancestral state of warblers was colorful, and that they lost that coloration and evolved a dull coloration in the fall to evade predators when they go to the tropics, when they migrate to the tropics. And then once in the tropics, they reacquire their ancestral color, and then they come back and breed in that coloration. So this wasn't a molt-centric paper. This was quite focused on the evolution of plumage. And I think because of that, they ran into some issues. One, their assumption is that the ancestral state of warblers was colorful. However, when you think about Humphrey Parks, if you think back to when we introduced this system, they suggested that this fall pre-basic molt that occurs after the breeding season is ancestral. It's shared by all birds. So there's a little bit of lack of parsimony here where Simpson is suggesting that this ancestral molt is giving rise to novel plumages. You would think it'd be the other way around, that you would have novel molts giving rise to novel plumages. So we think they're not mutually exclusive, these competing hypotheses. You can clearly have potential selective pressure, natural selection operating to generate dull plumages to avoid predation. But we think ours, the hypothesis suggesting that increased wear led to the evolution of the pre-alternate molt and was subsequently co-opted by sexual selection is the correct one. So that leads to this recent study, which I realize I didn't cite here. It just came out this past year in the journal Ecology and Evolution. And our objective was to determine whether the pre-alternate molt evolved to alter phenotype, as Simpson suggested, and as conventional wisdom suggested, or is it to replace worn feathers and was subsequently co-opted by sexual selection, as I suggested back in 2010, 2011. So for these methods, we collected a lot of response and explanatory variables from warblers. Pre-alternate molt extent, how many feathers they replaced, migratory distance, how far they migrated, seasonal dimorphism, sexual dimorphism. When I mean dimorphism, I mean how different are the plumage colors between fall and spring and between males and females. And of course, we controlled for phylogenetic relatedness. And the way this data collection went about was looking at a lot of museum specimens. Here's a chestnut-sided warbler where the bird was broken down into different feather tracts. And then each one of these feather tracts was scored for the extent of the pre-alternate molt, as well as different color changes between seasons and between sexes. And here's some of the results. So I know it's a little hard to read, but this is actually a phylogenetic tree of warblers on the left. And then on the right, it's actually the extent of the pre-alternate molt at the different feather tracts listed on the top. And so the brighter the turquoise indicates that there's more feathers being replaced. So if you go across the top, you can see that many of these species during the pre-alternate molt replace a lot of head feathers, a lot of breast feathers, a lot of belly, a lot of back feathers. In fact, if we look at each one of these tracks individually, it looks like this. So you can see on the y-axis, we have pre-alternate molt extent. On the x-axis, we have migratory distance. And a pattern arises that the head, the breast, the belly, the back, these are all highly correlated with migratory distance, meaning these are the regions of the body of the bird that are being replaced more frequently the further the bird migrates. So what's driving this pattern? This is a really distinct pattern. And we think that this is driven by the sun. These are areas that are absorbing the more solar radiation, and solar radiation is one of the leading agents of feather degradation among birds, in addition to habitats that might be abrasive. And in fact, so you might be thinking, well, why are migratory birds or longer migratory distance lead to more solar exposure? Makes perfect sense when you map it against day length. So here is some day length models from NASA. And if we look at January, so the lighter the turquoise, the more day length that these birds are being exposed to, right, by latitude. So if we look at the light turquoise, we can see in January, when if you look out your window in the Upper Peninsula, there's no birds around, right? A lot of these migratory warblers are in Central and South America. That's where we're having the most solar exposure of these birds. Come April, spring migration right now, they're moving north. So they're like, our warblers are probably just hitting Louisiana right now. They're starting to move north into the Midwest and look at where high solar radiation is. They're basically tracking the sun. When we get into July, right past the breeding season, into the pre-basic molting season, all the birds are in North America, and we can see that's where we have high solar exposure for these birds. October, come fall migration, as they're moving south, once again, they're tracking the sun. So the point being, if you're migrating towards the equator from North America, you're tracking the sun and you're being exposed to maximum amount of solar radiation to degrade your feathers. And in fact, when we plot day length here on the y-axis with the pre-alternate molt extent, we get a pretty tight relationship, right? So birds that are exposed to more day length are going through more extensive pre-alternate molts because the sun is presumably wearing their feathers down. So I'm going to go through some correlations just to show you how messy these relationships are before we tidy it up and get to take-home messages. Here, I'm going to show relationships between the various explanatory and response variables. The thicker the arrow, the stronger the correlation. So here, when we plot sexual dimorphism, seasonal dimorphism, they're closely related. When we throw in the extent of the pre-alternate molt, we can see that migration tends to drive migration distance, tends to drive the extent of the pre-alternate molt, which subsequently drives seasonal dimorphism. You throw in solar exposure and you have sun driving migration, which drives pre-alternate molt extent. This just looks horrible. It looks like a cat threw up a hairball on my computer. It's a bad figure. However, these kind of reticulate interactions between potential response variables, explanatory variables, drivers of phenomena we're interested in, like sexual and seasonal dimorphism, really lends itself well to path analysis. Basically, this is, I won't get into the details, but it's a nice extension of linear regression. And we can create different paths. Like what started first? Was seasonal dimorphism, was that a predecessor to migration, or did migration come first? We can create different paths and then see which explains more variance in the data and fit the models. So it would go something like this. If we created a path here where migration distance led to day length, led to pre-alternate molt extent, led to sexual dimorphism, we could use some of these phylogenetically controlled path analyses, and they would actually provide us with beta estimates and effect sizes, and we could interpret them. So long story short, we did this with a lot of different paths, and here's our top two models. And both models indicate the same path, that migration distance, right? Birds started migrating longer distances. That increased the day length or their solar exposure, which led to more pre-alternate molt extent, which led to more seasonal dimorphism and the evolution of their colors. So I think this analysis provides strong evidence that our hypothesis that we originally postulated was correct, that this is an elegant multi-step evolutionary pathway, that migration leads to more feather wear leads to the evolution of an inserted molt, that inserted molt was subsequently co-opted by sexual selection to result in these colorful plumages. Very cool, very elegant pathway. So, and just to back up, the conventional wisdom was there's a need for seasonal dimorphism, you evolved a pre-alternate molt. Simpson et al. In 2015 suggested that migration to avoid predation led to sexual dimorphism and the evolution of drab plumages. right? But not taking into account the evolution of molts. I think for warblers, and this might be exportable to other systems, this is what's going on. When you look outside your window and you see colorful birds arriving in the next few weeks, these warblers, this was the evolutionary pathway that led to those beautiful plumages that we really enjoy to look at. That they migrate long distances, that led to increased solar exposure, led to the evolution of pre-alternate molt, which was co-opted and led to seasonal dimorphism and sexual dimorphism. So the take-home message of this, before we can have like a more open conversation, is that molt is not boring. It's really fascinating, and it facilitates the evolution of novel phenotypes, which take up a lot of the oxygen in research, right? But molt is kind of this critical mechanism that's responsible for shaping some of these phenotypes, and this includes the seasonal patterns of colorful plumages that we cherish among our warblers. And so that's just a little insight to some of the research we've been producing. But I'll just end on one cool facet that I often meditate on, because I think it's equally as elegant as kind of this multi-step evolutionary pathway towards seasonal dichromatism. When you see these birds, like on the left-hand side, this bay-breasted warbler, in the center, this prothonotary warbler, when you see them arrive in the spring, they have all these different colors, and the browns and the blacks are melanins. That's the pigments. These are synthesized in the body and highly influenced by stress. If you look at the colors, those are carotenoids, and they're acquired through food resources, right? And those are influences, some links between carotenoid deposition and immunocompetency. So the point being is these colors reflect potential honest signals of the state of the bird when they molted these feathers in. Where did they molt these feathers in? In the tropics. They molted them in the jungles of Central America a lot of times, or in the case of prothonotary warblers, in the mangroves. And so they're carrying with them a badge of their disease, of their stress, of their food, a badge of their habitat quality in the tropics that they carry with them to our backyards. And then they're selecting mates based not on their phenotypes that they acquired in the United States or North America and Canada, but in the tropics. So it's this elegant connection across hemispheres of molting in plumages from the tropics, carrying it with them to North America, which drives their reproductive systems here. It's super fascinating and really elegant. Every time I talk about it, I'm like, I never get tired of it. Like it's almost poetic. So I'll end there, and we can open it up to questions. Janet, if you have questions, if folks have questions, or I have some topics we could talk about as well.
Absolutely. Oh, Jared, this has been so fascinating. And I have my own questions, but I'm going to hold off. So if folks are joining us for the first time, the way to ask a question is to use the Q&A feature and to just type your question in there. While you're doing that, I just want to take this opportunity to thank you both again for your time this evening. Sometimes the questions do go on for quite a while, and so thank you for patience. I did want to mention, because I know I'll forget if I don't do it now, that Husky, so those of you who might be coming to Michigan Tech for alumni reunion, well, guess what? You don't need to come. No, you can attend remotely one of the events through a Husky Bites live. So we're going to do an event on August 6th at 1:30, which is, we'll be featuring another pair of our faculty, I hope. And so you can look forward to that. We'll be posting that information on the website. So keep in touch, and around 1st of August, if you'd like to have another Husky Bites experience, you can join us. All right, so in the Q&A, so here's where I need your help, Erik. So because I won't understand any of these technical questions. The first few points are about the Moderna shot and whether our arms were sore and how sick we got. So yeah, I'm glad, Sid, you didn't get a bad reaction there. Yeah, no, so Ward, the robins are back. I think they got back about 2 weeks ago. I posted a picture of my first robin on my Instagram, but it was about 2 weeks, wouldn't you say, Jared?
Yeah, maybe even more. Yeah, maybe 3 weeks or more, the first robins started showing up.
Makes sense, because they left Louisiana about 4 weeks ago.
Yeah.
Well, and they're out there in the snow trying to find their, you know, the things that they're eating, because it's still actively snowing, and it's been snowing all day.
I love some of the statements. I much prefer to live in the alternative. Can we just jump in here,
Yes,
Janet?
of course, absolutely.
And feel free, Erik. This is like equally just jump in if you have any insight. But does a bird being held in captivity in aviary, does it affect its molting cycles? Most definitely. Particularly, people realized early on when they were studying relationships between circannual and circadian rhythms and molt, they would in aviaries, they would manipulate the light schedules to mimic changes in seasons, and they can induce different molts. And this really hit home when, if you guys ever go to the Monterey Bay Aquarium, for example, they have a number of shorebirds in that exhibit. And shorebirds often go through these pretty dramatic pre-alternate molts, and their plumages are just completely haywire. They don't match the seasons they're in. And it probably has a lot to do with the artificial light that they're subjected to. So being in artificial light, the birds can't cue up differences between day length, which ultimately sets some of the circannual rhythms that are responsible for initiating molt. So most definitely.
So that leads me to a question about the ptarmigan that you brought up. I actually didn't know that before, that they would roll in their own feces to mask their winter plumage as the spring is coming early.
Just rock ptarmigan, and there's just like one paper. Yeah, one paper. It might be the other ptarmigans as well, but rock ptarmigan is the species they documented it in.
Yeah, but and so, you know, these molts are very finely scheduled by day length, by changes of the season, and so, you know, climate change can affect the amount of snow, the cover, the available, you know, the emergence of spring. It can push that forward. And of course, the molt isn't going to necessarily adjust if it's controlled by day length. So it's a really interesting behavioral adaptation that's probably somewhere deep ingrained in their genome, but it may actually provide some, you know, some pre-adaptive benefit to deal with the effects of climate change with the onset of spring coming earlier.
That's a super interesting point. And this is super speculative, right? That's kind of the fun of these conversations.
Right.
Is climate change.
All hypothesis testing.
Yeah. There's climate change has been linked to increased cloud cover over the Gulf of Mexico, which has also potentially been linked to, which screws up some of the navigational cues that migratory birds use, right? They're using celestial bodies and stars. And as we're learning more, looking at some of the proteins that are found in bird's eyes seem to be sensitive to geomagnetic fields of the earth, so they have compasses as well. But one of the primary cues they use is celestial bodies. And so climate change potentially is creating more cloud cover in parts of the tropics, which might, in theory, reduce the solar exposure to these birds' plumage. I don't know what the cascading effects of that on average might have on, like, you know, the maintenance of some of these more extensive molts. There was a question here where, are there species with pre-alternate molts that do not migrate? Most definitely. They're pretty rare in North America, which is interesting, but there's some species that they became endemic to Adelaide's warbler, for example, to islands in the Caribbean, and they no longer migrate, but they probably once did, and they've retained their pre-alternate molt. So it might be like you needed migration and featherwear to initiate the pre-alternate molt, but once it's co-opted by sexual selection, that's a strong enough selective force to maintain that molt for sexual selection. But if you go to the old world, if you go to Africa, there's a number of species that are non-migratory, like widow birds, pintail whitas, which is a species that's actually expanding in California, where they'll go through a complete pre-alternate molt and they're not migratory. And so there's what we've documented among Nearctic neotropical migratory warblers might not be exportable to systems in Africa, for example.
I would add too, there's several species that we've documented from the central Amazon now that are resident non-migratory that appear to have pre-alternate molt. So Laniopulvis shrike vireo in the tanager family is a canopy species. And so it's exposed to really high levels of solar exposure, and it appears to go through a pre-alternate molt. We've definitely never found a pre-alternate molt in an understory forest species in the Amazon. But there's other groups like Spirophila, the seed eaters. A lot of these tropical grassland birds also seem to exhibit pre-alternate molts, which again, probably related to solar exposure.
And this is funny. So maybe the model does work. So you think about the examples that I gave: widow birds, whitas in Africa, they're in grasslands. So there's high solar exposure throughout the year because they're often distributed through the tropics, which may have resulted in the need for a pre-alternate molt because of feather degradation, which then they go through these, if you haven't seen these birds, Google them. They're gorgeous. They acquire these amazing alternate plumages. So Erik might have corrected me. There's actually, maybe that's this model of kind of a multi-step evolutionary pathway towards colorful alternate plumages occurs in Africa and resident birds too. It just only can occur in high solar environments that's very abrasive as well, like grasslands in the tropics. So
I know, I was gonna say there's 16 open questions, but I just have a material science question. Is there any shape change associated with the with molting, right? So is there, the feathers get longer so they can fly the big distances, or is there anything associated with texture or density?
There is as far as I know, yes. So two things, and Erik is an expert on this. So jump in here when I'm done, Erik. During the pre-alternate molts of warblers, there's a tendency for some of the coverts, and the coverts are their feathers on their upper wing. To me, they appear less structurally sound often. They're more downy and white and showy. And that hasn't been vetted, but it's just something I kind of notice when you open a warbler and it has big white, inner greater or median coverts from a pre-alternate molt. To me, they seem less structurally sound, but that might just be my bias that white feathers appear less structurally sound than black feathers. But where you do find the big difference is when birds molt out of their juvenile plumage. Juvenile plumage, depending on the species, is often longer, and so juvenile plumage is grown in the nest. If we're talking about an altricial bird, it's grown in the nest, and then they'll go through a molt shortly after leaving to replace this poor quality plumage. And that plumage is often shorter, but there's exceptions to that rule. Like Manicus, a genus of manakins, it's reverse, and I don't know why, where the juvenile plumage is longer than the subsequent adult plumage.
And it's different feather tracks too. So in some cases, the primary coverts are shorter in the juvenile plumage than they are in the adult plumage, but then the primaries are reversed. And so in Jared's model here with the pre-alternate mold, it typically doesn't involve feathers, like the primaries or secondaries or tail feathers. So we're just talking about the body.
Okay.
Yeah, so you don't see changes in wing length because those are the wings that were retained from the previous fall.
Got it.
But yeah, there's these age-related differences, and there may even be from year to year, depending on the bird's availability or access to food or food quality, may affect their actual structural change from year to year. So an individual bird may have a wing that's either 5% larger or smaller, depending on the year. I think that area of exploration is ripe for study. We've seen some anecdotal indications of this, but it's really hard to pin down because you have to track birds year after year and have very, very precise, repeatable measurements, which can be hard to do in the field.
So when you guys are walking around and you find a feather on the ground, pick it up and examine it, tilt it towards the light, and you'll see very faint, black, dark, and light barring. And those are called growth bars. And you have to hold it at the right angle to see it. And the light represents one night of growth, and the dark is 1 day of growth. So together, one band is 24 hours of growth. And there's a field called Telechronology where you can actually measure The Erik did a lot of this for his master's work, I believe, or is it your dissertation? I forget. Erik's done a lot of it.
Both.
Where you
I
can
did it for both.
both, where you can measure the amount of feather growth and determine how long it took that feather to grow. And what you find is if you have like a perturbation to a system where there's a dry signal and that results in like less food for birds when they're molting, those growth bars get really tight. And that so it takes longer for birds to replace an individual feather. And birds, particularly in temperate zones and maybe in the tropics as well, but less so, they're seasonally constrained, right? They have this life cycle that they have to fit in: breeding, migration, wintering, all the molt, and they don't like to overlap life cycle events. They do on occasion, but they don't like to because it's too taxing energetically. So oftentimes and maybe this is really complex kind of physiological decision-making processes that the birds have to do. If there's a strong signal that, man, conditions suck and I can't grow feathers fast, they might not grow them as long. That's totally speculative, but I wouldn't be surprised if that was the case. If you went into an area and collected feathers when there was a drought, they probably on average would have shorter growth bars and they would have probably shorter wings.
All right, folks, you have 20 open questions. Go.
Okay, let's go one by one. With the increase of whiplash weather occurring in the contiguous United States, do you think this could have an effect with molts? Most definitely. We have a paper that we're working on right now where we're looking at climatic signals, basically measuring. And the next question is CJ Ralph, who's an author and a collaborator on this work, largely responsible for collecting some of the best data on Western birds out there, long-term monitoring of these birds to answer these questions. But we can look at changes in climate and subsequently changes in the molting season, and there's a very strong effect. So that's good and bad. Birds have the capacity to adapt their molting seasonality to changes in climate. When we look at Europe, and they're kind of ahead of us when it comes to examinations of changes in climate, on life cycle phenology of birds and the consequences on demography. They find that birds that can't adapt their life cycles to changes in climate, those are the ones that are facing serious population declines, which makes sense. They're kind of like, they don't have the behavioral plasticity or the evolutionary capacity to keep up with changes in climate. So they're suffering demographically from that. So, but the birds that can adapt tend to do better, at least in Europe. A cardinal and CJ asks, why are tropical birds usually so colorful with your model? There's so many dull tropical birds, CJ, as you know.
Wood creepers. Birds.
You just took the pictures of the colorful ones?
Yeah. Well, that's what people focus on, colorful birds. But there's a lot of drab birds in the tropics, and the colorful ones tend not to have pre-alternate molts. They're just colorful year round. Erik, do you want to take this one? A cardinal.
Can I take the cardinal one?
Yeah, go for it. Go for it.
A cardinal is brilliant red. Does it molt into a dull color pattern during part of the year? So a cardinal is non-migratory, right? So, and it's a temperate bird. So immediately we would put it in the category of probably not having a pre-alternate molt, right? So Jared's model is indicative of the pre-alternate molt becoming more extensive with migratory distance. So if you're a non-migratory bird, then you probably don't molt. But there are other mechanisms for changing color throughout the year. So a cardinal actually, when it molts in the fall, does tend to be a little bit duller than when you see it in the spring. And that is because the edges of its feathers, particularly in the back and the coverts, are tinged in brown. And so it kind of gives it a slightly muted appearance. And then over the course of the winter, those brown edges wear off. And so when you see a cardinal in the spring, it is nothing but red. Obviously, the black mask is a different thing, but they do actually become brighter in the spring. It's very subtle, but it's true. That's even more pronounced in a few other species like eastern meadowlark and the common European starling. So the starling will molt in fall, all of its feathers, and it becomes that black bird, but with white spots all over it. And when you see a starling at this time of year in the spring, it's lost all of its white spots, and is this shiny, greasy, black looking bird. And it hasn't replaced a single feather. It's just worn off the tips of its fall feathers, revealing kind of a shiny undercoat.
Awesome. We love cardinal questions. Here's one
Yeah.
from Manuel talking about a paper on the evolution. And folks who don't know, there's like the Molt crews turning out in force. Manuel runs a great station outside of Veracruz in Mexico, bird banding station. Joseph published a paper on evolution of molt in regards to climate change. Did you see an extent of PA changing regards to migration distance for some species? Manuel, I don't think we have that level of resolution yet, but I think particularly for folks like you in the tropics and like Costa Rica bird observatories and who band throughout the winter, like documenting the extents and the timing of the pre-alternate molt is going to be really fascinating. That data might already exist at your banding station to look at changes in the timing and the extent of the pre-alternate molt in Mesoamerica with regards to climate change. I'm glad Robert Mulvihill asked this question. Robert Mulvihill is like a grandfather of molt limits, and he's kind of we've done a lot of work built on his findings, so it's great to see Robert here.
That's wonderful. Hey, I'm going to jump in with a question from one of our alumni, one of our Michigan Tech alumni. This is from Darwin. Is there any physical evidence that solar radiation degrades the feathers, such as making them brittle or reduces the feather's ability to shield the bird from solar radiation? So it's about physical evidence. Is it the sun? Is there erosion? Like what happens to the tips of wings of planes?
Yeah, really good. And I'm not like an engineer when it comes to like the understanding kind of at the molecular level, the structural integrity of feathers. And one of the reasons I'm so excited to be here at Michigan Tech is actually collaborating with the engineers. I think this is going to be the next step, is bringing some of juvenile feathers, alternate feathers, basic feathers into a lab and subjecting them to different tests to test their structural integrity. I think this is going to be a really rich field of research that we're going to be pursuing over the next few years. But I would suggest this, that I know from experience, and this is known by most bird banders, people who work with birds in the hand, that feathers are comprised of the rachis, which is the shaft, barbs coming out that you can visibly see, and then barbules that lock the feathers together. The density of the barbs seems to be age related. If you're an older bird, the barbs are more dense and they don't wear as fast. And I think that has to do with the surface area of the feather, that as younger birds, they have less dense barbs, and that opens it up to sunlight getting into the interior of the feather, dirt, grit, and they seem to wear more rapidly. And in fact, that's like a technique that birders use to differentiate, or bird banders, field ornithologists use to differentiate young feathers from old feathers, juvenile from adult. So juvenile feathers wear more rapidly. But as far as actually bringing feathers into the lab to test them against salt, pollution, sun, other potential agents of degradation, to my knowledge, it hasn't been done. It's a really cool field of research. But no, great question. Really great question. Robert Mulvihill asked about, can you give me a reference for the barball origin of black flecking? So Robert, I hate to put Chris Tonner on the spot at Ohio State University. He's a professor, but he studied American redstarts in Jamaica, I believe. And he's the one who documented this. And I've asked him for his citation, and I don't think he has it. It's just like an anecdote from his work. And maybe if you and I email him, we can pressure him into writing this up. But the mechanism, American.
Uh-oh.
Can you guys hear? Can you hear me now?
Now, yeah.
So American redstarts, they don't have a pre-alternate molt. The young males don't look like adult males. So they go through what's called delayed plumage maturation. It takes a year for them to acquire their adult male plumage. What Chris found on the wintering grounds was these birds go to the Caribbean, where they overwinter in places like Jamaica, and they hold territories like they do on the breeding grounds. And these territories are often contested among the different individuals. So what happens is the birds in the best quality habitat will have to battle it out to competitively exclude other birds. So if you're a dominant young male acquiring good territories, you're going to get in more fights with other males. This is all according to Chris. And when they fight, they rip at each other's face and chest. And so the feathers don't come in like that female type plumage, they come in black like an adult male. So the more black flecking means the more fights they were in, which presumably means the better habitat that they were acquiring in the Caribbean. So really cool. So it's like a bar brawl induced pre-alternate molt. And I passed the buck to Chris Tonner because I don't know that system, but he's the one that told me about it. I found it super fascinating.
It's so funny because I'm an engineer and like I understand all the engineer jargon and all that kind of, it's so funny to realize that there's such a deep technical language for all these, all the things that you study. No.
Oh,
and Erik, you get to choose a question next and answer it. We still have 15 open questions.
Okay, well, I'm glad this is simulating so many questions. Well, so Mike Bishop writes the next one. Don't most of the tropical species of warbler exhibit an alternate and basic plumage that are the same? So like the myobius warblers, if that's the case, wouldn't that help support Simpson's hypothesis? My understanding is that they don't. They just have a pre-basic molt and they don't have an alternate plumage.
That's my understanding too.
But if that's not true, I'd be interested to see the data. The one, I mean, I haven't studied that many non-migratory warblers in the tropics. Phaeophlipus rivularis is one that I know pretty well from the Amazon, and it's a relatively drab warbler. But as far as I can tell from all the banding data, it doesn't seem to have a pre-alternate molt. But that's an example of one. So.
And Mike, I tried to touch on this, and I think you bring up a good point that like Simpson's hypothesis and our hypothesis aren't mutually exclusive. Like you can have selective pressures that drive the retention of drab plumages in the fall to escape predation. Like that's totally in line with then the evolution of a pre-alternate molt because they're wearing their feathers down during migration. So they're probably both playing a role. Go for it, Erik. You want to take another one?
Yeah, I think we kind of talked a little bit more about red start. So I hope that satisfied Janica. So I'm going to skip to the next one. Gina asks, is there a correlation between how colorful the second molt and the distance traveled? Is there a geographic pattern between how different males and females are? And I think by the second molt, I'm not quite sure if that means the basic molt in this case.
Yeah, I think the second molt is like I think I get the question, Gina. Basically, that the further you go, will that ultimately result in? We know it results in more extensive pre-alternate molts, but does that also result in more colorful seasonal dimorphism and sexual? On average, yes, but it's not clean. So like the correlations between distance traveled and the extent of the pre-alternate molt is really tight. That's a tight correlation. But then once that molt evolves, the amount of dimorphism between the seasons and the sexes is less tight. It's necessary. It's a necessary component, but just because you evolve that pre-alternate molt doesn't necessarily mean you're going to evolve these brilliant plumages.
So the one question that I had that I hadn't really thought about before as you were presenting this, Jared, was does the pre-alternate molt more likely cause the carotenoid-based plumages over melanistic-based plumages? So if you're a bird that's got 50% melanin and 50% carotenoid in their feathers, during the pre-basic molt, is that more or less likely to shift to a carotenoid-based plumage in the spring?
That's a super interesting question. I don't know the answer to
Because
that.
it would be interesting to explore that, and relative to your hypothesis about the structure of feathers versus, you know, obviously to our eyes, the big yellows, the reds, and the oranges are all very beautiful, and obviously warblers tend to decorate themselves not only with that, but with the contrast with the melanins.
Yeah, I mean, I would also suggest, I don't mean to take us off the rails, but there's another system developed by Rick Prum, who's a professor at Yale University, where we try to, we're often adaptationists when it comes to like beautiful plumages. We're like, well, that must be an honest signal. And oftentimes there's evidence that it is, right? An honest signal meaning that beautiful plumage reflects something meaningful, like they didn't have diseases, they had good food, right? They have like good genes, like they're fit individuals. But Rick Prum has pioneered this field of non-adaptive sexual selection and even maladaptive sexual selection, meaning that, and here's just a brief example, and this kind of touches on Robert Mulvihill. I can see he's curious about plumages in tropical birds, but there's a species of manakin called club-winged manakin. And if you guys are interested in reading about this, Rick Prum recently published a book, I think it's called The Evolution of Beauty. It's really fascinating stuff. That this club-winged manakin does a display where it's beautifully colored and it clacks its wings above its back. And it does it very fast. You have to use a high-speed camera to capture it all, and it makes a rattling sound. And songbirds have hollow bones for obvious reasons. They're adapted for flight. This display is so dramatic that they're adapted to the display, and they've evolved solid bones. But the females that are presumably selecting the males for this, it's such strong selective forces that the hollow bones now are like reticulate in kind of the evolution, where the females, because they're selecting the male so strongly for this flight display, now they have solid bones. So it's almost, that's not a positive. That's like a deleterious trait that they're chasing or pursuing because it's beautiful. I mean, there's no other word. It's anthropomorphizing, but it's beautiful to them. And that's amazing too. Like it's not always like an honest signal. Sometimes animals and wildlife and birds, presumably people too, find something aesthetic or pretty or beautiful, not because it reflects some underlying fitness, like, oh, you have good genes, just because we like it. And sometimes it's detrimental. Like the birds now have solid bones because they're pursuing this particular trait. So I just mention that because when we see beautiful warblers, like the photos that I showed, there's probably some amount of non-adaptive sexual selection going on that we don't know. And it's, for me, it's almost like spiritual. Like there's something in the ether and a universal aesthetic that wildlife's pursuing that we can't quantify. It's just beautiful to them, you know? Anyway, I think that's a cool system. If you guys are interested in it, look at Rick Prum.
Oh, it's fascinating. All right, I'm picking up another question from an engineer. What % of birds worldwide do not molt? All right, I think the answer to that is 0 because of the first slide. Yeah, I learned something today. Well, and so is annual molting, which all birds do, is that for because they need to replace their feathers because of wear and tear? I mean, is that the basic fundamental reason?
Go for it, Erik.
Yeah, I mean, that's certainly the thought. And Jared posed this to me years ago when we were, you know, back in grad school. You know, not all birds breed every year, and not all birds migrate, but every single bird molts every year. It is that fundamental to being a bird, that they all do it. So I don't know if that really answers your question, but
no, it's helpful.
For one reason or another, it is that important.
So I've approached like and I'd be curious, Robert Mulvihill probably has insight to this as well. There's one paper that I know of that documents skipping a molt cycle. So that doesn't mean they don't molt. It just means they skipped it. And it's a group of geese, either from the Shetland Islands or the Falkland Islands. But it's like weird insular group of geese that occasionally they won't molt once a year. And then, and you know, in ecology, there's exceptions to all these rules, like constantly. You can talk about, there's why probably laws are so rare in ecology. Like there's not many ecological laws because they're always being violated. But this seems to be a pretty strong one, that birds molt every year. There might be large gulls that maybe skip an annual molt cycle. But when I say skip an annual molt cycle, it means they don't do it for 2 years. They do it maybe for 1 year.
Yeah, but there's also potential other mechanism, they may just not adhere to an annual cycle, right? Their cycle may not follow the calendar year. And as an example of that, there was a bird in the Amazon, white-plumed antbird, little songbird, smaller than a cardinal. It takes 300 days for it to replace all 10 of its wing feathers. And so, it's when we catch these birds in nets, only 50% of them are actively molting. And so you do the math, and right, so the annual cycle therefore is 600 days. Unless we're not catching birds that are molting, there's other sorts of things, but even so, I don't think they follow an annual cycle. They're just kind of randomly dropping one feather at a time in a sequence, and they can stop that molt and breed and do other things, and then they just continue it on. So I think, our understanding of seabird molt and I mean, I would love to learn more about those data to see if it's really that it's maybe just a protracted or suspended molt going on there versus just skipping a molt altogether.
That's a really good point. And I think Erik touches on larger kind of environmental pressures on birds' life cycle phenology. Like when they breed, they molt. When you move closer to the tropics, and this might also be true with like coastal effects, like in maritime places where it's much less seasonal, than inland places. There's fewer seasonal constraints. So you're a little bit at more liberty to being like, well, I'm going to extend my molt cycle or my molting season, like this white-plumed antbird he's talking about in the Amazon. But if you get up here to the Upper Peninsula of Michigan, you don't have that luxury. You have to abide by the seasons. And so the life cycle events become much more structured. It's kind of like you get down to the tropics and everything's like more like free love and free expression, and they can explore temporal space with their molts and breeding seasons. They're not adhering to these strict regimented seasons,
But some of the birds, when you look at the overlap of molting and breeding, it seems to be like very much related to different families of birds. And things that even in the Amazon, species and families in the Amazon that separated molt and breeding are the same families that we see here in North America. Whereas the wood creepers, the antbirds, all of those families that were, exploring these spaces of molt and breeding and overlapping them, those are the species that are restricted to the tropics. They never made it out. It's almost like there was a pre-adaptation of having a really structured life cycle that allowed certain species or certain groups of families to get out of the tropics and be successful in temperate systems.
Well, that's fascinating.
There's lots of questions. I'm kind of leaving it up to you guys to pick
Sure.
pick a question.
I'll take a couple, Erik, then you can take a couple. So Judy, why don't the youngest birds, the ones that just hatch, molt their wing feathers before they have to migrate this long distance for the very first time? Aren't those feathers crucial in migration success as opposed to body feathers? So good question. I would suggest, and there's actually a lot of gray area here, and you kind of touched on a point that I don't feel very comfortable addressing, other than kind of a speculative answer, and Erik can touch on it a little more. So birds in the nest is a horrible place to be. Like, you're fixed, you can't move through the environment, you're subject to predators. So birds need to leave the nest as quickly as possible. And that's why when you're watching a nest, the parents are feverishly shoving insect and protein-rich food down that nestling's throat to get them to molt, and they molt at once. The trade-off largely is that the quality of the plumage suffers for the speed of the molt. So they're molting fast, they're molting at once. And then they can leave the nest and be free in the environment. If you're stuck in the nest, you're going to get hit by a snake, another bird, a mammal, whatever. So the birds go through a secondary molt called the pre-formative molt, aptly named, once they leave the nest. Those replace presumably the critical feathers necessary for that bird's survival. Those often do not include flight feathers. They include body feathers. And what must happen is that the flight feathers in the nest, they invest more resources into making strong flight feathers and less resources into making good body feathers. Because a common pattern is that pre-formative molt that replaces those poor quality juvenile feathers, they typically don't replace the flight feathers. So we can just assume that the best balancing act of allocating resources towards which feathers to replace in the nest or to invest energy in, they're investing in flight feathers and not body feathers. But once again, go ahead.
There's a time constraint there too, right? Because the season, right, the season of energy of food resources is limited. And so when you're migrating south, it's early in the fall, there just simply isn't enough time in some cases to go through a whole nother molt and replace those. So what Jared is saying, I think makes absolute sense. Yeah. That in the nest during that first pre-basic molt, they're investing a lot of resources disproportionately into their flight feathers. There are other situations though, where some birds do actually replace those flight feathers. And when they do that, they tend to only replace the outermost flight feathers, the feathers that are most crucial for flight. And it's a sequence of feather replacement that is very unique to that first fall molt, that pre-formative molt, and we call it an eccentric molt in the molt literature. So you only replace like those outer 3, 4, 5, 6 outer primary feathers. So there are like weird little tricks that some birds have figured out how to get around, so they don't have to replace everything with just the most crucial feathers.
Yeah, it's there's also some neat a few key papers that pre-formative molt that occurs after the juvenile plumage, that's highly variable, as Erik was talking about, and that also seems to be the extent of that molt seems to be largely determined by seasonal constraints. Birds that hatch later in the year and that are in less seasonal environments they replace fewer feathers than birds that are hatched earlier in the year and in less seasonal environments. So it seems like the nature of the molt, how many feathers you're replacing, is largely determined by seasonal and energetic constraints as well. I'll do one more and then kick it over to Erik. This is from Robert Mulvihill. If the pre-alternate molt is an inserted molt resulting from the need to replace solar degraded feathers, do we see this molt especially well developed and extensive in non-migratory birds of equatorial regions? We were talking about that a little earlier, Robert. I think Erik pointed out, and I agree, that the model might be exportable where you have birds, particularly in tropical grasslands. So the seed eaters, Sporophylla, the widow birds, the whitas in Africa, they go through a pre-alternate molt that's quite extensive. And in some of those birds, their phenotypic change from season to season is also quite extensive. So I wouldn't be surprised if the model that we worked out for warblers is also exportable to those tropical grassland systems. I think I have to answer the next one, Erik, because it was a question about the map. What season, this is from Carolyn Peterson, what season did the heat map of bird diversity reflect during the breeding season? How would North America compare to the Amazon? The Amazon is actually quite variable in its species richness. So if you go to the Western Amazon, to just outside the foothills of the Andes, in places like Madre de Dios in Peru, Tiputini, the Yasuni Biodiversity Preserve in Ecuador, which I think the Yasuni in Ecuador is the most biodiverse terrestrial system on Earth. It's bewildering. Nothing's comparable to the amount of birds that you can acquire from a single location. If you move towards the eastern Amazon, diversity starts going down, as well do the number of large birds, which is interesting. This is a general rule, but like, for example, on the western Amazon, you'll get these great birds called in the genus Neomorphus, the ground cuckoos, right? They're like, imagine psychedelic version of a roadrunner that runs around in the understory following ant swarms. Really cool. As you move out towards the central Amazon, they get fewer in number until you get out to the eastern Amazon, and they blink out entirely. And there's a whole lot of speculation about what drives that diversity gradient from the western to the eastern Amazon. But when you get to North America, some of the highest breeding bird abundance occurs in the Appalachians and the Great Lakes regions. I mean, we live in the UP in a fantastic place for breeding bird assemblages. It's really quite amazing. I don't know if you have anything to add, Erik.
Well, and I would add to be careful to distinguish between alpha and beta diversity. So there's some evidence to suggest that as you move into smaller and smaller and smaller scales within the Amazon, that alpha diversity actually is fairly consistent between the Western Amazon and the Eastern Amazon. But you do lose some of these charismatic megafauna, particularly like ground dwelling, fruit eating birds, which may be related to a productivity gradient, or you just have like less fruit available in the Eastern Amazon. But I think by and large, like alpha diversity is not as different in the Eastern Amazon versus Western Amazon than beta diversity, the turnover in diversity as you move, each kilometer away. And that may just be because of like really high habitat turnover in the Western Amazon compared to the Eastern Amazon, which is a little bit more uniform.
There's some, this is totally speculative, but just talking with people who spend a lot of time studying Amazonian biogeography, there's some people that suggested, and you see this too, in forms of salt licks. If you go to the Western Amazon, salt licks are at a premium. I mean, some of the best places to find macaws and parrot species, like in Tambopata in Peru, are these massive salt licks. Like clearly the systems and the wildlife are hungry for salt. As you move to the east, salt, you find fewer salt licks, and that might have something to do with like the ambient patterns of precipitation or wind blowing salt off the ocean potentially. But you also, and this is completely speculative, you find, you hear people talking about runoff from the Andes, that it might be a little bit more silt and nutrient rich, even though there seems to be plenty of silt in the Amazon. Maybe it's not silt, it's nutrients coming off of that that ground and degraded bedrock coming from the Andes into the Western Amazon. And there's some magical mix of nutrients, stable climatic conditions, rain and sun that provide massive biodiversity. That being said, is like there's just very briefly how biodiversity arises in the tropics. It's probably a result of, and there was a recent paper came out a few weeks ago in Science supporting this, that that they're not subject to the glaciation events like you have in North America. So there's stability of environments and climates over time. So you can have species arise, like evolving speciation events, but they tend not to go extinct in these lowland tropical rainforests, particularly the Amazon. And it results in like species packing. The further north you get, you'll constantly have turnover, or glaciation events and whatnot, knocking back habitat, species going extinct, and then you have to reset the clock for evolution to kick in. So it might actually be a difference of extinction events across latitudinal gradients that gave rise to the incredible diversity you find in the Amazon.
All right, we're coming up on 7:10, and we always call a hard stop at 7:15. So Erik, why don't you pick out one more question that you could answer, and then after you finish answering it, maybe some concluding remarks from you, and then Jared will have some concluding remarks from you. And right now, here's some concluding remarks from me. Thank you so much for joining us. I've had another amazing evening where I actually learned things that I really knew nothing about. And I want to ask, so many more birding questions, but with that, I'm going to turn it over to Erik. And thank you everyone for joining Michigan Technological University for our weekly webinar series called Husky Bites. Join us Monday nights in fall and spring at 6 p.m. Eastern Standard Time. Erik.
Can I take the question about ectoparasites?
You bet.
It happens to be a little niche specialty that I've dabbled in. So the question is, well, first, great talk from David, Jared. You mentioned solar and abrasion as consequences for feather wear. What about ectoparasites in terms of their role and overall feather wear. Well, so in songbirds, most of the parasites are either lice or they're mites. Most lice do not chew on feathers on the outer part of the wing. They're usually embedded within the body feathers. But there is a special group of feather chewing lice that are specialized to bird wings, and they live kind of between the little barbules. Jared mentioned the rachis, and you have the barbs, and then you have the barbules. So these things live within, tucked within those little barbules, and they chew on the feathers. But all songbirds seem to have them. And there doesn't seem to be a huge consequence in terms of wear. It's probably a good explanation, or one of the reasons why birds have to replace their feathers once a year, but it doesn't necessarily seem to be related at all to at least in the flight feathers, the pre-alternate molt. What it does to the body feathers is a whole other question. But I will say there's a researcher at Arkansas State University, Thon Boves, who's studying the effects of feather mites on parulid warblers. So he's studying all these different parulid warblers like Jared was doing and looking specifically at mites. So it'll be interesting to see what he finds. So, and as my closing remarks, I'll just say, thank you to Janet and Jared for inviting me. Any hour plus that I get to talk about molt, particularly Jared, is an hour well spent. I always learn something. So this was a lot of fun, and I'll pass it to you, Jared, for the last question.
I agree. Thank you so much, Janet and Erik. I purposefully made the presentation short because I so enjoy chatting with Erik about birds and answering questions, and it's always fun. So yeah, if you guys have any further questions, feel free to email me. You can find my website and get in touch.
Oh my goodness, I learned so much again. There's still 20 open questions. I kind of feel bad. Thank you so much, Jared, for offering up your email. Do you want to just say your email address out loud?
Sure. Can I put it in the chat? Would people see it if I did that? Or
I'm not sure if they can see it. Just go ahead and tell it out loud.
Yeah, it's jdwolfe@mtu.edu.
And Erik's is eric.johnson@audubon.org. So I apologize. I feel like when there's this many open questions at 7:15, I feel like we should just keep going, but I also want to be respectful of our speakers' evenings. Thank you everyone for joining us. This is the last Husky Bites of spring semester. Those of you who want to join us again in the fall, we will start off the first Monday after Labor Day. And I forgot to mention this earlier. Yeah, we're going to be having a really exciting new fun series where students 9th and 10th grade can do a 4-week project with other people in the nation that's focused on sustainability. And on the 5th Husky Bites, I'm going to be walking through our sustainability house. No, a student is going to be wearing a head cam or something so we can explore the sustainability house here at Michigan Tech, which will be a lot of fun. Well, it's been awesome. Thank you so much. Good evening, everyone.
Okay, take care.